Yes. Do we have to hold something? Yes. Let's see. This is all right. Good morning, everyone. I'm Jan van den Brand. I'm going to talk about data structures for algebraic problems and how you can use them to speed up iterative algorithms, for example, linear program solvers. And well, data structures, right? They're one of these really useful tools in algorithm design because we can use them to make algorithms faster. Think of something like algorithm for minimum spanning trees, right? If we use Kruskal's algorithm together with the union find data structure, then the algorithm becomes a lot faster. And what I want to talk about today is like a subclass of data structures for matrix problems, for algebraic problems, which you can use to, for example, speed up algorithms for linear programs, but they're also widely applicable in basically any kind of iterative algorithm where you have to repeatedly solve some kind of matrix problem. So let me define a bit more in detail what do I mean by a matrix data structure. So here we want to fix some rational function f over the matrices. And what I mean by that is basically anything you can write down using the basic matrix operations. So multiplying matrices, adding, subtracting them, or inverting a matrix, all of that is allowed. So here we have an example for, oh, it doesn't have a laser. All right. So here we have an example for such a formula, right? We multiply two matrices M1 and M2, we invert the result, then we multiply a third matrix, and right, that uses only the basic matrix operations, so that fits this definition of a matrix formula. Now we want to have a data structure with an update and a query operation. So let's say we initialize on this formula here. So we have this matrix which we want to invert and multiply with a vector. Then right now we as a user, we don't know what the value is, the evaluation of this formula. So what we can do is we can query the data structure. We can ask, hey, what does this entry of the evaluation look like? And then the data structure will tell us that value is a 1. But we can also perform updates. We can tell the data structure, hey, this entry of our matrix, we want to change that to, for example, the number 2. Now again, we as the user, since we changed the input, we don't know what the new output looks like. So we can again perform queries and ask the data structure, what does the resulting vector here look like? And you can perform more updates and more queries. And the hope is that if you have a data structure for such a formula, then whatever iterative algorithm you have, instead of just recomputing the value of that formula from scratch every time, you can use the data structure, which hopefully is faster. So then the algorithm will be faster as well. So that's roughly what I want to talk about today, how to use these data structures to get faster iterative algorithms. The first half is going to be about how you can just use existing data structures as a black box. So you don't need to understand how these data structures work. You basically just cite them and plug them into your algorithm, and hopefully it becomes faster. And then in the second half, we are going to open up the black box, look at how can you tailor this a bit more to your problem to get something even more efficient. And depending on how much time we have left at the end, I'm also going to talk about what happens if you have like especially tall matrices in your formula. How can you maybe do things a bit more efficient in those cases? So let's start with how to use existing data structures as some kind of black box. So existing data structures, right? So the problem was maintain the value of some formula under updates and queries. There is a data structure by Stankowski which says if you have something like P input matrices to your formula, and every matrix is of size at most n by n, they're allowed to be rectangular, but all the dimensions need to be bounded by n of all the input matrices. Then you can maintain the value with update time roughly Pn to the 1.5 and roughly Pn to the 1/2 query time. On the other hand, if maybe whatever problem you're trying to solve doesn't have a high dimensional output, if you only need very few queries, then there's also another data structure with a slightly faster update time, but a slower query time. All right. And now I want to give an example how to use these data structures. So the high level idea is quite simple, right? You take an iterative algorithm And the first task then is to try to write the computation that you have to perform in every iteration as some kind of matrix formula. So you can apply these data structures. Then you just use one of these previous two data structures, and hopefully that's enough to make your algorithm faster. This approach works for a bunch of iterative algorithms. So for example, the Gram-Schmidt work, which is used for vector discrepancy, can be sped up using this way. You can get a fast algorithm for QR decompositions. In this talk, I will focus on the Simplex-Algorithm, since the title of the talk is Data Structures for Linear Programs. I want to outline how you can speed up the classic implementation by Danzig, which would need something like n² time per iteration. We can speed that up to subcritic time per iteration. Okay, so very quick recap, linear program and simplex algorithm, what is that? So our task is to maximize a linear cost function. So we have the C transpose times X, and the vector X needs to satisfy a bunch of linear constraints. So we have a matrix A and a vector B, and we want that A times X entry-wise is at most the corresponding entry in the vector B. And this set of linear inequalities defines a polytope. So you can kind of think of that as this geometric object here on the left. That's the set of feasible points. Now we want to find a point that's as far as possible in some direction C. And what the simplex algorithm does is it kind of just starts at one corner and then moves along the edges from one of these vertices of the polytope to the next until it reaches the optimal solution. And now what kind of computation do we have to perform here? So if you look at the actual implementation of like the simplex algorithm, what you can argue is that in every iteration, what you have to compute is you have to solve, instead of this system of linear inequalities, you have to solve a system of equalities. So you pick a subset of the rows, and for this subset, you now want to satisfy that this subset times X is equal to the corresponding subset on the vector B. That kind of corresponds to asking what point of the polytope lies in all these yellow highlighted facets of the polytope. So you kind of have one of these vertices. Now going from one vertex to the next really just means you replace one of these facets by another. In particular for the linear system, it just means you select a different subset of rows. You replace one of these rows by another in your linear system. And our task now is to rephrase this formula, this kind of linear system as a matrix formula. So how can we phrase the selection as a formula? What we can do is we can introduce some kind of selection matrix S. So that's a rectangular matrix which is really sparse. It's zero almost everywhere except for these diagonal entries. Right? And if you now multiply rows of S with the matrix A, you can see that it's really just going to select these top 3 yellow rows because all of the rest of A is going to be multiplied with the 0 entries. And you could just use the same selection matrix S also on the vector B. And now selecting different rows really just means, okay, you're going to move one of these non-zero entries in S from one location to another. So the summary here is that we have a matrix formula which tells us what its vertices are. It's the solution of this linear system. So we have S times A, we need to invert this, multiply it with S times B. So that's the formula for these vertices. And we observe that from one iteration to the next, we just need to change 2 entries in this matrix S because one of the non-zero entries needs to become 0 and one of the 0 entries needs to become a 1. So to summarize, what are we going to do, right? We have taken some iterative algorithm, in this case, the simplex algorithm. We rephrase the computations that have to be performed in every iteration as some kind of formula. We observe that we change 2 entries. And since we need to compute a vector, we need to read n entries of the value of this formula. And now we take one of these existing data structures, in this case, the one by Sankowski. And well, since we just have 2 entries that change per iteration, we just need to perform 2 updates. So we get n to the 1.5 update time per iteration. We need to read n entries. So we again get this n to the 1.5, roughly n to the 1.5 time for performing all the queries. So in summary, we now have a faster simplex algorithm, right? We now have less time required per iteration. And this recipe you can apply to a whole bunch of other iterative algorithms as long as you're able to write the required computation as one of these matrix formulas. Yeah. So I'm assuming that n is the largest dimension that occurs anywhere. So that would be the number of constraints in this case. Yeah. Okay, so this is kind of how you can use it as a black box. Now I want to look at how can you make this even more efficient. We open up the black box a bit. For this, the idea is, okay, instead of using one of these existing data structures, we now want to create our own data structure for one of these formulas. As an example, I want to give interior point methods. So, for example, the algorithm by Vatia back from the 80s needs something like n to the 2.5 time. I'm going to argue that using this approach, you can now get a faster algorithm that runs in current matrix multiplication time. This has been proven several times using slightly different techniques, but in a sense, the data structures all kind of fit into the framework that I'm going to present today. So very quick recap of interior point methods. As the name suggests, we start with an interior point, not a vertex. So here we have this orange dot, which is somewhere in the feasible space inside. And what we want to do is we want to move this feasible point on the interior of our feasible space until we reach the optimal solution. And you can show, when you analyze these interior point methods, that the direction in which you have to move is given by the following formula. It's this A times A transpose D A. You invert this A transpose times V. That looks a bit scary at first, but this matrix A is really just the constraint matrix that you used of your linear program. The matrix D is going to be a diagonal matrix, and V is some vector. And only the diagonal matrix and the vector V are going to change from one iteration to the next. So the matrix A here is fixed. And one can show, if you analyze this interior point method, that in total, you only need something like linear many changes to D and V, like linear many entries are going to change. And this method only needs something like root n iterations. Now, the first naive approach would be to say, all right, we have a formula and we need to compute this every iteration. Let's just use this black box approach again. And the issue now is that, well, we said we need something like n to the 1.5 time per update. And we have a total of n changes. So we need to perform n updates. So this cannot beat n to the 2.5 if we use this approach. So in this case, using these black box data structures is not fast enough. We need to kind of get something faster. We need to optimize it a bit. And the idea here is that, okay, wait a moment. We have n changes in total, but only root n iterations. So that kind of tells you that many entries are going to change all at once. But these black box data structures, right, when you perform an update, you just say, change this one entry. And then the next update is change the other one entry. So the hope is that since a lot changes at once, maybe you can kind of batch this together, process all of these changes at once to get something faster. And that is the idea that we now want to use to get a faster data structure. So let's summarize, right? We want to maintain the value of this expression up there. And we say D and V is going to change over time. And since this expression looks a bit scary, we first want to reduce it to like simpler problem. What we're going to do is we want to reduce this to the case where we just need to maintain an inverse. So we don't care about the formula anymore. It's just matrix inversion. And well, this matrix that we're trying to invert, that's the matrix that's now going to change over time. The trick we are going to use is that one can prove that for any of these matrix formulas, you can always find some large matrix n, which is a block matrix where you can just plug in all of the inputs of your formula. And this nice matrix n has the property, if you now invert the matrix, there exists some part in the inverse that contains exactly the value of the desired formula. So now we just need a data structure that is able to maintain this inverse, because let's say D changes, then you just perform updates in this top left corner of the matrix n. And if you want to know what the value is when you evaluate the formula, you just need to read the entries here in this blue block. And the nice thing is that this is not just true for this specific formula, this reduction works for any formula. Yeah, it's not just existential, the proof is actually constructive, yes. And regarding the complexity blow up is just that well, all the input matrices have to fit inside. So if you only have like a constant number of input matrices, this matrix n is roughly the size of of the input that you had already. All right. So how does this help us that we need to look at matrix inversion? Well, it turns out that matrix inversion, how this behaves when you change the matrix, that has been known since the 1950s already. So in the 1950s, there was discovered the Woodbury identity. This expression looks a bit scary. Let me walk you through this. What it tells you is, this is your matrix N, and you're going to change it, right? You're going to add something to your matrix N. Now you want to know, okay, the matrix N changed. What is the new inverse of this matrix? Well, the new inverse is just the old inverse minus some stuff that you have to compute. And well, what you could do is, well, you just use this identity to compute what the new inverse looks like. And in fact, that is how all of the old algorithms back from the 80s for these interior point methods use their data structures. They just use this identity to recompute the inverse. But the issue is that you can show that if you, let's say, change k entries of this matrix N, and you use this identity, you need this mnkn term. So this is the complexity of multiplying an n by k matrix and a k by n matrix. In particular, this is at least n squared time. And paying n squared time in every single iteration of your algorithm, that's kind of slow. So we don't want to pay this. So what can we do to make this more efficient? So let's look at the Woodbury identity in more detail. We said that we change some entries of the matrix N. Let's say we want to change k entries, which means we want to add some super sparse matrix to N, which is 0 everywhere except for these k blue entries. You can very quickly construct two matrices U and V that, if you multiply them, return this matrix. In particular, these matrices have the nice property that here every column of U has only one single non-zero entry. The same is true here for the rows of V transpose. And that makes the computation really easy now, because let's say we have this N inverse times U here. If you compute this product, since U is so super sparse, it's really just selecting a few of the columns of N inverse. Right? If you multiply a row of N inverse with a column of U, you can quickly see that you're just selecting these highlighted columns. In particular, you could implement this really efficiently by just using pointers, right? You technically don't even need to read the values from memory. You just say, okay, it's a rectangular matrix where this column is just that column over here. You just create a pointer. So it's almost free. And the same argument can be made here on the far right. So when you multiply V transpose with N inverse, you're really just selecting a set of rows. And in the center here, where we have V transpose times N inverse times U, you're just selecting both rows and columns, which really just means that you select these highlighted in blue, these the submatrix of the N inverse. Which means so far we didn't really have to do any real computation. We just create a bunch of pointers. The only real computation we have to do is, okay, I don't have a pointer, but there is this extra inverse up there. So that means this small submatrix that we have read, we actually need to invert this again. So there is a bit of computation we have to perform, but it's just inverting this k by k matrix, which is something like k to the omega time. So that can be done quite efficiently if k is small. Now let's say we have our new inverse in this representation. We have all of these matrices in memory. How can you now get one entry of the new inverse? Let's say we want to know this yellow entry of the new inverse. How can we compute this? You just take the corresponding entry of the old inverse and need to multiply the yellow vector with the yellow matrix and this yellow column vector. You just multiply this together. You have the new entry. In particular, reading one entry just needs k squared time because you just need to multiply with the small k by k sized yellow matrix in the center. All right, so updating and performing queries if k is small is fine. But now when k gets larger, paying k squared for a query might be kind of slow again. So what we could do is we could use the two rightmost matrices and just multiply these two together during the update. So when these k changes happen, you perform one more step. You multiply the two rightmost matrices together, so you kind of have this representation of the inverse. And now reading an entry is more efficient because you no longer need to multiply with this yellow matrix, you just need k time to read one entry. On the other hand, your update cost gets a bit more a bit larger because you had to multiply the two matrices. So you had this k by k matrix, which needed to be multiplied with the k by n matrix. So you need to pay at least nk time. And another approach would be, all right, what if we just multiply these two blue matrices together as well? Then you pay even more during the update, right? You pay at least n squared time. You basically just multiply everything together, compute the inverse explicitly. But now you can read an entry of the inverse in constant time because you already computed it. So you see kind of that there are three different ways how we can use the Woodbury identity. And you kind of get a trade-off between paying more in your update or paying more in your query cost. All right. In particular, if you look at this and think of what happens for like a different k, if k is really small, right? If k is small, then this option S is going to be beneficial because if k is small, this is almost free. Paying k squared doesn't matter because k is a small value. But if k is really large, then you're better off using this option L because, well, if k is like close to n in value, then you might as well pay n square anyway during your update and get the super fast query cost. So this is why I'm going to call this option S, option M, and option L because they're kind of the best choice for small k, medium k, and large k. And this interpretation of the Woodbury identity immediately implies a data structure because you just say the following, all right, fix some threshold parameter t. Let k be the number of changes we had to the inverse since the last time we computed the inverse. So in every iteration, we check what is k. When k is larger than the threshold, well, k is large, so of course we want to use option L. On the other hand, if k is less than t, then it's kind of a small k, so we use option S, and then we needed to query one column of the inverse. And that's basically it. So the question now would be, all right, we need to do some kind of complexity analysis. We need to know how often do we come into this branch where k is large, how often do we come into the branch where k is small. But that really depends on basically what kind of iterative algorithm you're currently trying to speed up. In case of the interior point method, you can show that some batch size of value L, so let's say k is equal to L, that happens at most root n over L times. And you could now do the calculation. It's a bit boring, so I'm going to skip it. But if you use this property, you can use the complexities from the previous slide to argue that this is going to run in current matrix multiplication time. All right. So the summary here is that if you want to create a data structure that is more tailored to your problem, what you can do is whatever formula you have, reduce it to matrix inversion. Then there exists the Woodbury identity, which actually has these three options on how you can use it. And now there are different trade-offs for these options between update and query time. So you basically just need to mix and match that depending on what your outer algorithm requires. Do you need a lot of queries or are your updates really large? And that really depends on your outer algorithm. In case of these linear program solvers, using something like option L for large K and option S together gives you this current matrix multiplication algorithm. But it turns out that this approach is internally used in a whole bunch of other papers as well. So for example, this black box result that I used earlier for Simplex, this is the result by Sinkowski. Internally, that algorithm does actually the same thing. It uses option M and option L together. And in case of linear programs, all of these current linear program solvers, they can be phrased as they're combining different options of the Woodbury identity. So this is a really powerful technique to get fast algorithms. Okay, how much time do I have left? 10. All right, good. So we have a bit of time to talk about tall matrices. So far I just bounded all the complex, even more. Yeah, question. For the previous one, you would need a special IPM that really needs a few changes to the matrix. So it depends on what kind of interior point methods you use. Depending on that, the size of K in each iteration will be different. Robust IPMs have this property that I stated. general interior point methods back from the 80s have that in every iteration you would change at least n entries. All right, so far I bounded all the complexities just with a single parameter n, but matrices, they have two parameters, right? Besides of the height, you also have the width. So what could happen is that you have kind of tall matrices that are really thin. And the hope is maybe you can get something faster now, because if D is small, then maybe since the matrix is kind of small, then you get a faster algorithm. But these reductions that are used so far, they're really inefficient for that. Right? You have to construct some large matrix where you can embed your matrix A, but later we want to invert n, and you can only invert square matrices. So if you try to embed a really tall matrix into n, n also must become very wide. So you're losing all of the benefit that you might have for these skinny matrices. So this approach that I talked about so far is more efficient if you have almost squarish matrices. For tall matrices, you need to do something else. I want to briefly sketch how we do this in the case of these interior point methods. So the idea is to just split our data structure task into smaller modules. So our task, right, was to maintain the value of this formula up there. Here I represent this formula as boxes. So each box is a matrix. And let's split this into smaller tasks. So at first we need to multiply A times V. In every iteration, we have to multiply these two matrices, this matrix with a vector. But that can be maintained very efficiently, because what happens is, let's say one entry of V changes, then it's only going to affect this one column of A transpose. And that means you can maintain the result by just paying D time for every entry. And if D is small because it's the skinny matrix, then that's almost free for one change. Next, after you maintained this product, you have to multiply with this matrix in the center. But it turns out this matrix is only of size D by D. You can maintain it via Woodbury and leverage score sampling, which Omri is going to talk about more tomorrow. And it's a D by D matrix, so you only pay D square for a product. And we said D is a small parameter, so let's ignore that for now as well. The main bottleneck comes from the fact that at the end, we have to multiply the resulting vector with this A again, and A was the tall matrix. In particular, you would usually have to pay something like ND time in every iteration to multiply this. And N is the large dimension. We don't want to pay N in every single iteration. So how can we fix this? So we want to use linear sketching. The idea here is, okay, we want to compute this vector W, which is A times some vector. You're going to use some sketching result, which says that there exists some random matrix R with the property that for any W which you multiply, it kind of compresses the vector down into some small dimensional Y. And I say it's compressing it because you can also decompress it again. Given this Y, you can reconstruct this W tilde up there, which entry-wise is really close to the original W. And that can be used now to speed up the computation with this product with A, because once during the start of your algorithm, you just pre-compute R times A, which kind of compresses the matrix down. Now, if you multiply your vector with R times A, you get this small dimensional Y. But what you have here, right, is basically the compression of the result of A times H. So you can decompress it again to get some approximate W. So you have an approximation of A times H. And the interior point method turns out to be robust enough to handle the approximation errors of the sketching. And that's how you can get then these fast linear program solvers for tall matrices. So the summary is that I talked about some generic way how you can use existing data structures in a black box way. There you don't need to know how these data structures work. You basically just need to write your iterative algorithm as something that needs to re-evaluate some formula involving matrices over and over again. I gave as an example that the Simplex-Algorithm can be sped up, but other iterative algorithms could be sped up like this as well. I also talked about how you open up the black box, how you can optimize the data structures a bit. The idea here is that whatever formula you have, you can reduce it to matrix inversion. Then just use the Woodbury identity, these three options on how you can use it, with a bit different trade-offs depending on how many entries change all at once, or do you want to pay more during update or more during query? So you really need to mix and match that depending on your specific algorithm. And as an example, I gave that the interior point method for solving linear programs can be sped up from n to the 2.5 to current matrix multiplication time. And at the end, I said that, okay, for tall matrices, if you want to exploit the structure of these tall matrices, then you cannot use these previous techniques. Instead, it's going to be more useful to kind of split your problem into smaller parts, so you can exploit that maybe intermediate results have small dimension. And whenever you have to handle large dimensions, try to use sketching to get rid of this large high-dimensional object. All right, thanks. So the sketching works for any vector, not for all vectors at once, no. For any vector, it works with high probability. And in particular, it means that it's something that an adaptive adversary could exploit. What you can do there is, so how we solved it is we first sketch something, but then we verify the result. So the output is kind of deterministically defined, but with high probability, we return this output using sketching techniques. How small does it get? So for us, what happens is every 2 to the I iterations, we have a sketch size of 2 to the 2i. So technically, we have multiple sketches that are used. Well, the higher the sketch dimension, the less frequently we use it. So amortized, it's still fine. For this, so as long as you basically just change one entry in your matrix formula, which would mean you replace one column by one other column in the simplex algorithm, it doesn't matter what pivoting rule it is, then you can use this technique here. Right. So if you have a very tall matrix, you kind of get into this problem I talked about at the end. If you have a tall matrix, the data structure scales in the largest dimension. So if your linear program has lots of constraints, but very few variables, then the classic implementation, I said it's n square because I just used one parameter, but it would be more like n times d. Yeah. You can get n times d. I think you might even be able to get something like d squared plus sparsity of the matrix, but I would have to check again. Yeah. But for the tall case, we use the Lee-Silford barrier, which has root d iterations. If you're fine with a small complexity blow up, you can actually use the log barrier as well. The complexity would then match rectangular matrix multiplication of n by d by d. So you can get something that's also fast using the log method, but it's a bit slower than using the Lee-Silford barrier. Right. So all of this relies on fast matrix multiplication. This idea of using like these different options of Woodbury, at some point you always need to use this option L to kind of reset. If you don't use fast matrix multiplication, then that part is basically going to crush your amortized complexity. And in that case, you could just as well just use the classic Woodbury explicitly every iteration. Well, it does use fast matrix multiplication. I was told that Strassen is used in practice. About these specific data structures, I honestly don't know. So updating the matrix using this Woodbury identity has been used in practice. So the old algorithm by Kamaka, he has actually written code, and I think he actually ran this at Bell Labs. On the other hand, I was told, so I can't verify this, but I was told that Woodbury would be kind of numerically unstable in practice. From a theory perspective, we assume that everything is well conditioned, so you just need polylog many bits. But from a applied point of view, you don't always have polylog many bits, right? You have 64. Yeah, Richard. Sorry, I need to come closer. I see. So the good question. So for the interior point, this IPM result where I say it runs in current matrix multiplication time, I think that should also be true for if you use Strassen. But you probably also have to use Coppersmith's rectangular matrix multiplication algorithm. But I think that depends on the same tensor or something, so it shouldn't be much worse than Strassen in practice. So you should be able to solve linear programs in n to the 2.8 or whatever the exponent is of Strassen's fast matrix multiplication algorithm. Yeah. Yeah. So that one is right. That one does not use Strassen. Yes, that one does already use fast matrix multiplication. Yeah, if you don't use fast matrix multiplication, it should be n cube, I think. If you use a data structure, yes. Is batching used in practice? I mean, it's kind of automatically used in the sense that, yes, many entries are going to change at once. But if you don't use fast matrix multiplication, then batching your updates or processing them one by one has the same complexity. There could be that there is a difference in constant factors, which I assume in practice matters, but I don't actually know. Like, I never implemented these things. Right. So in practice, these short step methods are not used usually. They use long step methods, which from a theoretical perspective have a worse iteration bound, but in practice, they just converge after, I don't know, 38 iterations. And But if it's well conditioned, then you can just use a conjugate gradient descent or something like that. I've recently read a paper where it was stated that near the end of the interior point method, the condition number can get a lot worse. But I don't know how in practice people go around that. Yeah. All right. Thanks, everyone.